Hi, so I'm doing this as a video instead of a written post for a reason. I want you to actually stay with me on this one because I think the message matters more than the technical details I'm about to walk through. And before I start, let me be clear about something. I'm not making this video to brag or throw around deep technical terms. I'm not claiming to be an expert as well. But what I am is someone who believes that foundations matter, first principles matter, because when you understand the foundation, you start to see patterns, you start to connect things, you start to understand where everything actually came from and why it works the way it does. And if you're anyone working in applied AI, anyone building with these tools, I think it's worth your time. So stay with me. Some of this might get a little bit technical. That is okay. Just let it sit. Even if it does not click all right now, the point will land. Okay, coming to the topic. So I read Sundar Pichai's CloudNext post earlier this week. Lots of really cool stuff in there. 16 billion tokens per minute through their APIs. 75% of new code at Google is now AI generated. Pretty wild numbers. But one line in his post stopped me. Google announced their 8th generation TPUs. Now, if you do not know what a TPU is, no worries. A TPU is basically a custom chip Google built specifically for AI. Think of it like a GPU, but designed by Google for Google. It is what trains and runs models like Gemini. And here's the thing, for the 8th generation, they have completely two different separate chips designed. One chip is called TPU-8T, built specifically for training. Another chip called TPU-8i, built specifically for inference. Two different chips for two different jobs. So I sat with that for a minute and asked the obvious question, why? Why are training and inference so different that Google is willing to design and build and support two complete separate chips? Okay, first a quick refresher. What is training and what is inference? Training is when you teach the model. So you show it tons of data, it makes predictions, you tell it where it was wrong, and it slowly adjusts itself to get better. Inference is when the model is already trained and now you are using it. You ask it a question, it gives you an answer. That's it. On the surface, these look like the same thing. Both are just a bunch of matrix multiplications running under the hood, on the chips. But they are very different jobs. Let me break it down. So in training, the model has two passes. A forward pass where it makes a prediction, and then a backward pass where it figures out how wrong it was and updates its weights. That backward pass roughly doubles the compute you need. And the chip has to remember everything that happened in the forward pass so that the backward pass can use it. So training needs a lot of memory. Whereas inference is just the forward pass. You feed in your input, you get your output. Done. No going back, way less memory. Then there is precision. This one is interesting. So in training, you are nudging billions of weights by really tiny numbers. If your chip is not precise enough, those tiny numbers just disappear. They round to zero and your model stops learning. So training chips needs high precision math. Inference does not have that problem. The model is already trained. The weights are set. You can round them off pretty aggressively as well, and the model still works fine. Which means inference chips can fit way more compute into the same space because lower precision math takes less silicon, more speed for the same power. The bottlenecks are different too. In training, you have thousands of chips working together, and they all have to talk to each other constantly to stay in sync. So the bottleneck is usually the network between the chips. Whereas in inference, especially for chatbots and LLMs, the model generates one word at a time. And for every word, it has to pull a large chunk of data from memory. So here, the bottleneck is memory speed and not networking. And finally, the economics. Training is something you do once. You spend a ton of money for a few weeks, you get a model, you're done. Whereas inference, it runs forever. Every single user query, every single day for years. So with inference, you obsess over cost per query and how fast you can respond. So when you put all of this together, you start to see it. A chip designed to be amazing at training is honestly wasteful when you use it for inference. A chip designed for cheap, fast inference cannot handle the precision and memory demands of training. Okay, now here's the part I really wanted to get to. This is the reason I'm making this video. We are living in the age of generative AI, LLMs, agentic systems. The pace is honestly wild. New model every week, new framework, new abstraction that promises to make everything easier. But in reality, it doesn't. And it is so easy to lose the plot. It is very easy to just treat the whole stack as magic, to build stuff on top of layers and layers of things you do not really understand. For me, I keep coming back to first principles because the why teaches you much more than the what. When you understand why training needs higher precision, you make smarter calls about quantization. When you understand why inference is memory bound, you stop guessing about batch sizes. When you understand why Google split their chips, you start to understand why your own serving costs look the way they do. Like I said at the start, this is not about showing off how deep you can go technically. It is just about staying grounded. Think about this for a second. Everything we work with today, every LLM, every agent, every multimodal model, all of it started from a single perceptron, just one artificial neuron. You take some inputs, you weight them, you add them up, you apply an activation function, you get an output. That's it. So you stack a few of those into layers, you get a multi-layer perceptron. Make it deeper, you get a deep neural network. Add convolutions, you get the vision models that do image recognition. Add attention, you get transformers. Scale up the transformers massively, you get LLMs. Wrap those LLMs in tool use and memory, you get agents. That is the whole arc, from one neuron to systems that can reason and take actions in the real world. The abstractions on top get taller every year, but the first principles underneath, they do not change. So if you're anywhere in applied AI, especially if you're early in your career, here is my one ask. Go one layer deeper than your job strictly needs you to. You do not have to go all the way down to silicon. Just one layer below, wherever you currently operate. That is where the real intuition lives. And honestly, I think that is what separates people who chase trends from people who actually understand what is happening. That is it. Thank you so much for staying with me on this one.